When we start designing our own classes, we need to be sure that we're creating logical combinations of operations. The Java API is a great source of inspiration for an aspiring Java designer. Let's take a closer look at some classes that we've been using for months, with an eye towards designing our own class as well. The string class is a particularly interesting class in Java. You've probably been thinking to yourself that string objects are just arrays of characters. And that's correct, sort of. But the string class has a secret you probably haven't guessed, unless you've experimented with string objects. You certainly know that two string objects that contain the same characters will be equivalent using the dot equals method. So if we have string name1 equals Abby and string name2 equals Abby, system out println name1 dot equals name2. What you may not know, however, is that these two string references are actually addressing the same object. There's really only one string literal that contains Abby, and both of these string references are pointing to it. If we do system out println name1 equals name2, we're comparing name1 and name2 using the equals operator, and we'll get true. But it's even more complicated than that. What will happen if we construct the strings using the string constructor that takes a string literal? So we do string name1 equals new string Abby, and string name2 equals new string Abby. This should work the same way, but it doesn't. These two strings are dot equals to each other, just like the other string literals. They are not, however, equals to each other, even though they were constructed from the same string literal. If you look at the Java API for constructor in the Java class, this is coyly suggested. We know the string class as well as we know any class from the API. We've used it all over the place for a full semester, and yet it has the secret. Let me tell you what's going on in the string class. Now, the real details are beyond the scope of this class, so I'm lying to you a little bit, but you'll get the main idea. The string class is keeping track of an array of string literals. Suppose we've used the literals Mary, Mary, quite contrary in a program. The literal table will then contain these strings. If we use quite again, the array will be searched to find if quite has been used. If it has, then the reference to quite in the table is returned. If it hadn't been used, it would be added to the table. Java even lets you decide that you'd like to do this with string objects you create, using the intern method. If the string is in the table, the reference will be returned. If it's not in the table, it'll be added to the proper place in the table, and then its reference will be returned. Now, this is an advanced programming technique, so you may not want to use it just yet. Sometimes trying to be efficient too soon can cause problems. People have some pretty strange beliefs about efficiency, and sometimes things they do to try to be efficient make the program less efficient. There's a saying in video game development, for example, that premature optimization is the root of all evil. It's a bit of an exaggeration. However, professional video game programmers generally believe that it's better to find bottlenecks in the code and work on improving the real bottlenecks rather than trying to guess where they might be in the future. You may be wondering why I'm finally spilling the beans on the string class after months of secrecy. It's to make a point. The string class, one of the most carefully constructed and heavily used classes in Java, is so successful at concealing its inner workings that you had used the class for months before you discovered its secret. This is a particularly poignant example of what's called encapsulation. A detail of the string class was successfully hidden inside the class. People who used this class had no idea how it was working. Now, we've seen other examples of encapsulation. For example, we studied array list objects before we studied arrays. So we had no idea how the array list was keeping track of the things that were added, deleted, replaced, and shifted around. We drew pictures of what we imagined it to be. Not surprisingly, some of these pictures looked a lot like what we now recognize as arrays. These are outstanding examples of successful encapsulation. Let me give you another example of encapsulation. How, exactly, does data get written to a hard drive? We've done it with the scanner class. But this class uses regular expressions, yet another really amazingly neat part of computer science that we can't really talk about just yet. But even beyond that, hard drives rotate around. Writing to them involves getting to the right track, waiting for it to cycle around to the under the read head, and the time to let the disk rotate so we can read the data. We haven't talked about any of these things, even though we've been writing data out to hard drives for months. What's more, some of your computers probably have solid-state drives, so the details of writing to those drives are completely different. But we didn't use a different Java class to write when our computer had a solid-state drive instead of a rotating disk drive, because writing to the hard disk is well encapsulated. Encapsulation has a long history in computer science. One of the most influential early books on software engineering, The Mythical Man-Month, Essays on Software Engineering by Frederick Brooks. Now, you can tell it's old because it uses man-month instead of person-month. Even has a chapter on encapsulation, although it's the only chapter in the book that's generally agreed to be wrong now. Brooks argued that there must be someone, somewhere on a project that knows all the details. We now recognize that this isn't possible given the large scope of today's software products. Encapsulation is necessary because the number of details in a program is so large. So when we design our own classes, we want to remember that the details need to be encapsulated. We really already have done this in one of our examples. Remember when we stored the phone number in the contact class as an integer, even though the constructor accepted a string? The storage of the phone number was encapsulated. Another design principle we need to consider is that we need to provide people using our classes with complete sets of operations. Let's consider a class like ArrayList. The reason that we were able to use that class for so many things is that it offers us a complete set of operations. We can insert items at the end or in the middle of an array list using add and add all. We can delete items using remove range, and clear. We can access individual items using get. We can modify individual items using set. We can search the array list using contains, index of, and last index of. We were even given some methods that control the resizing of the array that's hidden inside the class. If the group of methods was missing something we needed, we would have to write our own class instead of reusing ArrayList. As a general rule, classes need to have a way for people using the class to get data that is not encapsulated out of the object. In our contact class, we didn't have a method that returned the phone number and stored it as an integer, but we did have a method to return the phone number as a string. That counts. When you're designing classes, you need to consider whether someone using the class needs to be able to access every data element or not. It's okay to have some secrets, just like the intern table in the string class, but it has to be possible to use the class fully without knowing the secrets. Notice that our ignorance about interning string literals did not slow us down a bit in using string objects. Mutators are methods that change objects. Some classes have mutators and others do not. When a class does not have any mutators, it's called immutable. Some of our favorite classes are immutable. Integer, double, character, and string are all immutable. The string builder class, however, is mutable. Notice that it has methods like append, delete, insert, and replace. Determining whether a class in the Java API is mutable or immutable can require some detective work. Both the string and string builder classes are pretty upfront about this matter. The first sentence in the Java API tells it like it is. Remember, this is nice when you Java doc your own classes. So when should a class be mutable and when should it be immutable? That can be a tough judgment call. If your objects are constantly changing, they certainly need to be mutable. But if the object changes only occasionally, remember that reconstruction is always possible. As an example, most people keep their names consistent over long periods of time. Yes, some people do change their name, particularly when they marry, but that's really a rare event. If you're not sure that a class needs to be mutable, it's usually best to make it immutable initially. If you need to add mutator methods later to make the class mutable, you can do that easily without breaking any existing code. But once you've put mutators in a class, it is very difficult to backtrack and make the class immutable, because lots of code typically will have to be changed. If you can't make perfect decisions, and no one can, at least make decisions that can be fixed if they turn out to be an error. You may have noticed that in just a few months we've now gone from worrying about how to get individual lines of code to work to getting groups of code to work, like methods, and now classes and groups of classes. As you continue as a programmer and eventually become a software engineer, the process of arranging larger and larger groups of classes, called a package, and system components like databases will continue. Just as you learn to write letters, then words, then sentences, then essays and English classes. Each level of increased complexity brings its own unique challenges. The general challenge of software engineering will always be finding ways to do more and more complicated things that people in our society want to do with computers as elegantly, reliably, correctly, and securely as possible.